So here we are. We've got Dave. He won't stop. Here's his comment that he put up underneath our last video, because he's talking about this particular photograph right here and this piece down here. This is the first photograph on magazine 37, except there's one prior to it, and no way to explain how you could have one prior to the first photograph. So anyway, he says this is not the underside of the limb right here. He's saying this is inside, coming from this photo number, which had the suit and the bags on the floor next to it. So this is the photograph that he's talking about that he claims is coming from. This image right here is supposed to be out of this photograph, and here this is blown up from down here, but he's saying that's the photograph that this image is coming from. Well, of course it's not. He's making this excuse right here. That's the photo number 365399, and that's this one right here that he claims that that little clip came from. He doesn't explain how it's on that magazine when the first image is being shown.
Well, it's not.
I took this particular thing because this is where that image is coming from. That piece of material right down there, the ribbing along there, is coming right from this piece of the machinery right here. This is the opposite side from the ladder. The ladder is on this side. This is the flat panel with so-called all of the equipment in it. And somehow they managed during an Apollo mission to get up there with a camera to be able to take that photograph. And of course, the suit that is in this image, the piece of the suit, obviously is not being worn. Even if it is being worn, I don't think it's being worn. But it's up there. But how do you get up there? And even if you did manage to crawl up there, you wouldn't be able to get in there with a PLSS on. Absolutely no way you could get up in between those two pieces of material on that. And then, of course, that's not the only spot where you see a suit that's just laying around on the equipment. In Apollo 12, you also have this image of the suit with it just draped over the strut here. That's a piece of the strut, there's a piece of the strut, and it's just draped down there. That's the collar just of the outside of the suit. The red ring for the helmet is not on that.
Flip it around like you did before so we can just get an idea. It's ridiculous. That's foil. Look at the stuff sticking out of it.
That's the foil from the leg on it. That's the leg over there. Now it's flipped upside down, or you can do it from this angle if you want to look at it.
It's like they've taken the suit and they've just undone the zipper in the back and slid the hole where the head goes and slid it over the strut.
Yeah, and you see even the mounting box on the front where the camera mounts is removed, or a piece of it's been removed. That could be the mount for the camera right there. But that's just the foil from the secondary strut. And the other image of that shows the strut there, shows the strut there, the leg coming all the way down. That's the secondary strut there and there. So that strut and that strut are secondary struts, and they're showing exactly where it is. And you can see this material is not being worn by an astronaut. I mean, there's no possible way anybody, if they were on the lunar surface, could remove their spacesuit. That's just putting it right out there. Robert has pictures of the mapping they did on the lunar surface. When it was taking off from the Earth and it comes out to orbit, it does its translunar injection. It's coming off on an angle slightly above the equator. Like I think Apollo 11, it's anywhere between 5 and 15 degrees, something like that, between the different missions, where the moon is located in relationship to. So when they come out and do their orbit, they have to stay on that plane, the same plane when they're orbiting going around. Now, of course, CSM, so-called, is in rotisserie mode, yet it would have to stop being in rotisserie mode for the camera to shoot to the lunar surface, which would then cause heating and cooling problems with it. But the moon is orbiting at the same time. They can't go around and do these stripes like this. They go around the one time, the next time they come around, the moon's going to move a little bit, so it'll be a wedge, 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 and it'd always be running over a center point. So they wouldn't be in straight lines like that. And of course, Robert also has the panel where the camera was doing this mapping.
Yeah, so here is it rotating. It's supposed to be, this is just an animation, but it's rotating. Now look at this. This is the most ridiculous thing I've ever seen. You could reach right out that window and grab it.
Here's the model right here with the camera right on it.
Feelers here, right? They're rigged to go up to this sensor so it moves the camera up and down slightly so the lens doesn't hit the surface. And now here you go. There's your reproduction. And then you get this. Oh, this is even funnier than this. You want to tell us what this is?
Okay.
This is Apollo 10. It's quite long. It sits over there if it doesn't move.
If the craft is in rotisserie mode or barbecue mode,
why isn't it moving? They're 6,000 miles an hour. Why are they staying in the same place? They're not moving.
That camera that's running up and down the plaster mold, they just move it over and slide it down, move it over, put it back up, and that's how they get those nice, beautiful straight lines on the mapping images that they claim that they had. And that's exactly how it was done.
Do you know how many times this thing gets swapped out? They have a few of these things sitting on the side, ready to just plant in there.
And those ones aren't even really curved.
But then you look at the other one that was facing the opposite way. The camera was actually pointing up. How many simulators do you need? I think that's where a lot of the money was going, to these camera tricks, these parlor tricks.
Well, they had to pay for Lookout Mountain laboratories, didn't they?
I'm sure that they were developed in every location that they had. Even when they did the gloves, they put the bid out on 3 separate contractors produced gloves for them, right? And they would have done the same with this. Who could come up with the best maps?
Yeah, because they had as much money as they wanted, didn't they? Unlimited budget.
Yeah, there was just no end to it.
But these guys are going to have to stop that rotisserie to get this.
Yeah, they are. Exactly.
And then they got to stop the moon from rotating.
Well, they can stop the moon from rotating if it's just a model stuck on a floor somewhere.
Oh, you know what? We have a treat for you.
This is what can be done on a phone. Starts right there. He zooms in to the moon. This is on a phone. Right to the landing site. And right to the footprint. There are people that will believe that their phones can do this.
Amazing what technology can achieve these days, isn't it?
Yeah, well, like, some people will believe that.
I know, yeah, they will.
And quite a few people, like many kids, they don't know anything. They just think that's the technology today. Oh, you can zoom right into a footprint on the moon. And that's up on TikTok.
And this is the thing, is that people say, well, we can't see it. You can't see anything from the Earth-based telescope, no matter how big it is. And these people are going to say, oh, well, I saw it on TikTok.
Imagine what a multi-billion-dollar simulator can do. You're on the lunar surface. Are you measuring 12 meters back?
No, you're not.
Can you set the camera to 74 feet?
To an extent you can set it 74 feet. You'd probably set it at infinity.
There's the instructions for the camera, how to set it, right there. But how do they know it's 74 feet? These cue cards were designed months before they got to the moon. How do they know the astronaut is going to be standing exactly 74 feet? Why not 75 feet? Or not? Why not 70 feet? Or why not 80 feet? How does he know he walked out from this object 74 feet?
Because that would be the instructions to the set dresser.
The set design is designed, take the photographs, 3 photographs here, 3 photographs here.
Yeah.
20 degrees off, you're 50 degrees off from the sun. I don't know if it's 3 photographs, 1, 2, and 3, or it's 3, 3, and 3. I think it's 1, 2, and 3, just 3 separate photographs out there. How do you know that this is far field photos? How do you know you selected the rocky area? How did they know months before? Because they had no idea what landing site they were going to be on.
And also don't forget that Armstrong, we're told, had to fly the craft about 4 miles beyond the anticipated landing site. So where they actually landed hadn't been examined. He was landing in completely different areas. So these cue cards, which were written before they took off, we're told.
You know, Apollo 11 doesn't actually have cue cards. They did get away with that. But these instructions here, photos taken is a past tense. Oh, by the way, they're still doing soil erosion from descent stages, landing, erosion cratering and stuff underneath the engines. In Hawaii, up to date, I have got the documents.
It's about 50 years too late.
Yeah, but why are they still doing tests today?
Because they're listening to what we're saying. They're listening to the deconstruction you and Robert and the rest of us have made about the explanation that they have come up with, that NASA have come up with, never a straight answer, and they're realizing they have to change it because otherwise it's going to get too obvious. I think it's become too obvious.
This cute little note right here, EO, and you will see it in here when you're coming back through. They've obviously handwritten this in after they had printed everything out. And then here's EO again, and then here's the explanation of what EO is. Enthusiastic observations. Those are acting instructions.
Enthusiastic observation, I love it.
Well, it says right there, every time they put a little EO in, wherever they want them to be enthusiastic,
Yeah.
Get up to the edge of the crater and be enthusiastic about all the stuff you see in there.
Yeah, jump up and down and wave your hands. Drive close to rim. I don't know where the rim was.
I'm surprised you don't see MC for medium close-up or medium close-up, wide. All those different terminologies that they use. I mean, I remember one video that I was in, a music video in 1992, and we were sitting in the editing, and all that we were doing was going over all these doggone MCs and Cs, and but every time you come to a part in the editor, I remember Nick had the notepad, and he would always write the time down with the close-up, medium, or far, or wide, or whatever it was that he had in there, right? And then we'd go back and review it. To know where to put the video together and what sequence to the storyboard. This is just about the same thing. That's the only thing that's missing.
Here we go. We're going to start on this part right here. It says start. And it says, gyro. You're going to update Houston on your gyro. You are out 1 hour and 25 minutes into this mission, just on the EVA, because each of the EVAs start at 0 time. They're not part of the overall time travel. So 1 hour and 25 minutes, they travel for 17 minutes to get to this elbow crater. It gives instructions on what the crater is all about. The mounds, it's got a raised rim, levee. It describes block distribution. I don't know why it's called a canyon crater, that one, because this is elbow crater here. These little X's over here on this side are where they walk in and stand to take the photographs, where they're supposed to stop and stand and take the photographs, each of the X's, when you see that. They're asking them to pan from rim. So they want them to do a photographic sequence, panoramic, across the rim of elbow crater, and asking them for enthusiastic observations while they're doing that. So that gives them the time that they're traveling through right here. It shows them from where they travel to the elbow crater to the geological station number 1, which is 7 minutes to that observation. There's the timeline again, showing to go to station 2. How do they know? How do they know how long it's going to take them? This is months before these are prepared, and these are typed out for them to practice with. There's absolutely no way they would have any idea how long it would take to go from one to another. Any little object on the ground could stop them from going. They might have to go on a big loop. They might have to go around anything. They could bump into soft soil. Even a little ridge that they wouldn't be able to drive the rover over would cause them time. They can't possibly have this time in and be in sequence. And it's exactly in sequence. Every one of the cue cards is exactly the same. Timeline here is exactly right to the minute. And you keep looking through. At 3 hours and 50 minutes, they're going to park the rover, and they're going to be heading southeast, facing the equipment bay, but I think it's quadrant 4. So it's just on the inside, on the shady side of the ladder, basically, where they're parking that.
Yeah, but wouldn't you be enthusiastic? I mean, let's face it, you're going up to this crater, And they're telling you, be enthusiastic, but you don't really need to be told that by any director, because once you view what's down in that junk pile, you're going to get pretty enthusiastic trying to figure out what the heck it is. And that's with every single one of these craters. Every time we've looked in these craters, that's all we see is just man-made junk everywhere in there.
But they have all of these instructions in there for the camera, for the TV camera, and then it just says point the high gain, it says point to Earth. Well, you need to call the guy to get it to point it to the Earth. These are just little things they could practice wherever they're practicing, right? And of course, most of the scheduling says that we're at Flagstaff with Farouk Albez. And when you go through these, right back to the very start of it, right? Yeah. The instructions are so basic out there, and they just follow this through. They don't go off of this, anything that they're doing there. They should be stopping, checking the pressure on their suit. And of course, they have to have their buddy check the pressure on their suit because it's up on their back to see how much stuff. There should be a gauge to show how much battery life they have left. They need a gauge to show how much water that they have in their system is, right? And what the internal temperature of the suit is all the time. None of that's in here. They don't check it. They just follow through this thing because it is the storyboard on which they are to follow.
It's a storyboard for the films. It's not scientific. Basically, it's the way Hollywood would do it. It's really what Tom Hanks did when he filmed Apollo 13. He had a storyboard for it.
Yeah, it wouldn't look much different than this.
No.
Those cute little things that put in here, the enthusiastic observations. I mean, if that doesn't tell you what this is about, that's just beyond belief that that's actually in there. And of course, when you look through all of the cue cards, you're going to find that all the camera descriptions, angles, distances are there throughout all of them. You're going to find out these X's show them where they're going to be standing. Even one of them says, take a photograph of the disturbed soil where they moved a rock. Well, how would you know there's going to be a rock there? How do you know you're going to disturb it? And how do you know you're going to take a picture of the disturbed area, the rock, and your footprints? If you don't know, you're going to take that. All of these things are in the cue cards all the time.
Oh, it's good stuff, that. You've got the detail of it, which is important.
Well, it's probably one of the biggest, of the many, like you could take an entire list of what defines this and shows that there's fakery involved. Those things would not happen. Every one of the details is far too precise, and they've spent a lot of money and energy and spent the last 50 years trying to defend themselves doing it. The details that they come out with on the travel from the entire storyline was laid out. Every minute is accounted for. And now it caused a problem, because now you have to include audio conversation that you can't possibly put in there, because there's no audio conversation between the astronauts, because there are 3 astronauts, not 2. And when they pick them up, even their landing sites, I mean, they're right down to the minute when they're going to return. That's all part of the storyboard. The cue cards are part of the storyboard. The transcript is part of the storyboard. All the audio files they put up are part of the storyboard, and the photographs. You put them all together, it makes a nice story, and people can believe it, but it's all fiction.
People do believe it because they want to believe it. They want to believe that America was the first to land humans on the moon. Well, you can believe that if you want to. I believe in 3 things: Father Christmas, the Tooth Fairy, and the Easter Bunny. For everything else, I want evidence. And the evidence for the moon landings by humans is sorely lacking.
I was watching Jay Leno interviewing on tour at Elon Musk's facility. Obviously, Elon Musk was saying things that they don't want because the video's been removed. But the little piece that we got, there's about a 10-minute piece there. The one piece I was interested in was Elon Musk is saying, he said, getting to space is easy. Getting into low Earth orbit is 100 times more difficult. Now, space is, to Elon Musk, is 50 miles, not 62. 50 miles.
50 miles, yeah.
Okay. Low Earth orbit is 100 miles. So if it's 100 more times difficult to get to low Earth orbit in today's world. Don't forget, Musk has been doing this longer than NASA. He's been doing it twice as long as what NASA had time for to do the Apollo missions. He's been at it that long. And he didn't start from scratch because he's in today's world. He has today's technologies. If they want to build a rocket engine, they know how many foot-pounds of thrust it's going to put out because it's a robot building the thing and it's exact. They're not hand-built. They know exactly what that thing's going to test at. And he's had time to build many of them and test many of them. And he knows what that output is. So now you can put the information into a computer and do the calculations on what your acceleration rate is, everything else. They got the air temperature, barometric pressure, the whole 9 yards down pat when they're going to take off. They know what the acceleration force is going to be and what the air drag is going to be. Plus, they can do it on simulators 1 billion times over. The computer can do it repeated until they get exactly, work it out. They know they're going to be so accurate doing that. The guidance systems are going to help them. All of the other efficiencies are going to help them, and the weight's going to be less because all of that equipment weighs a whole lot less. They've got sensors to pick up any sensors to vibrations, you name it, coming off the machine, and they know where the weak spots where they need to reinforce it. They can put sensors all over the machine, and they know where the structural plane needs to be. So they can trim the weight down where they don't need it. They didn't have all of that in the 1960s. They just set a rocket off and it either worked or blew up. And they had no idea why. They go back to the drawing board and you got guys with slide rules. Yeah. Today you got sensors on everything. So you know what's going to happen. You know what the tensile stresses are. You know the acceleration forces and the G forces and everything else and the temperatures. Right? And you know you got the sensors, you got cameras to go with it. So you can see it as well. Elon Musk has had all of this equipment. He didn't bring people in that didn't have experience. Apollo started, they didn't have people building rockets for human spaceflight. It was all brand new to them. They have people. They've got computers and software and simulators and all kinds of stuff. And he sits there and says, it's 100 times more difficult to get into low Earth orbit. Imagine what it would take to do then a trans-lunar injection.
Well, so far as I know, Musk has only done one mission beyond low Earth orbit, which was when he sent his car to Mars. And we saw all pictures of it.
We don't know anything about what his car is doing or anything else because the camera went off. Battery in the car, and couldn't keep the camera running for more than a couple hours. But yeah, all of that stuff. But if it's so difficult, even today, for him to achieve and launch a satellite, just a satellite, into low Earth orbit. And he says it's 100 times more difficult just to do that than it is to get to space.
Well, space isn't very far away. As you say, it's 50 miles.
Well, they call it at 50 miles, right? They're in space. So to go to 100 miles is 100 times more difficult. How much more difficult? How much more fuel? How much more technology is it going to take to do and control? Like today, we've got equipment. Certainly you can hit the moon if you needed to hit the moon. But to get the trajectory just right with a limited amount of fuel that you have, to get to the right speed, the right angle, the moon's moving, it's orbiting, the Earth is moving. You've got to work all that out. A computer can do that today. But now you have to have the fuel to be able to do it. Plus, it's got to be protected through the Van Allen belts and the whole 9 yards. And what people don't understand is when you get to space, you are just simply out of the atmosphere. You're not out of the gravitational pull of the Earth. You're not even close to it. Like I said, if you took a basketball and you put a dime on top, that's low Earth orbit. That's as far as you are away off the planet at that particular time. The gravitational drop is so little, you'd barely notice it. Considering the fact that the Lagrange zone, the L zone, for the Earth to the Sun is 1 million miles out. And that's when the gravitational pull of the Sun and the gravitational pull of the Earth are equal. And that's 1 million miles out. So if you think you're going to eject off, you're still accelerating from the gravity of the Earth the same as you are taking off. The only thing that's different is you don't have any air drag. There's no atmospheric drag. But when you're 10 miles off the Earth, there's very little atmospheric drag because there's very little atmosphere already. Not to mention the fact that things are rocket, like they're designed like a bullet, so that they have very little drag to start with. But imagine like 10 miles off, and there's basically no air drag on that vehicle anymore. Right? Even at 5 miles off, you're already down to 5 psi air pressure at the height of Mount Everest. At 5 miles off the Earth, the air drag's dropped down. At 10 miles is virtually nothing to worry about. That's not where the problem is. The problem is still the gravitational pull. And that pull's going to be there until you meet up with the L zone between us and the moon, where it changes. You're always going to be slowing down. To go from 50 to 100 miles to low Earth orbit is 100 times more difficult. How much more difficult is it to do a translunar injection? And I do not believe that any manned mission has ever done that.
Unmanned missions are different.
In the last 20 years, yeah. I wouldn't go back more than 20 years. Because they need the guidance systems.
Yeah, they do.
They have to be autonomous guidance systems, and that didn't happen until 2002.
So
That IBM 750 that they put out.
So what about the lunar orbiter?
We were just looking at the camera that did the lunar orbited mapping.
Yeah.
Yeah?
There are so many questions that arise when you start looking into it as deeply as you've done, as Robert's done. You start looking into it that deeply. There are so many questions that arise that are reasonable questions. I mean, they're not conspiracy or anything like that. They're just straightforward scientific questions. If that happened and that happened, how did that happen? It's different.
Why are they just up and running? And that's in Hawaii, by the way, all this testing they're doing for the cratering for a lander. Which means that they're going to be able to put together something that will be able to land on the moon.
Eventually, yes.
Eventually. But they're still doing the testing and the soil samples to see how much cratering there's going to be.
You see, that's what I mean about, they do that now. So the obvious question is, well, didn't they do it 50 years ago or 60 years ago when they were creating Apollo? And if they did, why do they need to do it again?
When Apollo so-called landed, it didn't do anything to create a crater. So why would it be a concern? If all of the excuses that NASA has got about there isn't a crater there, and don't forget, what they're doing testing on is maybe a 6 or 7, maybe 800-pound robotic machine that's going to be landing. What was Apollo total weight when it landed? I think it was still, 13,000 or something?
I believe it's about 3 tons, which is, 7,000 pounds.
The takeoff weight was 3 tons. And then you still got the entire frame of the lander.
Plus all the internal support systems.
And those 60-kilo batteries.
I
Those would be the first damn things I'd be throwing out the door. They're used up. Get rid of them. You're going to be, 20 minutes up there to get loaded and gone. Get rid of these 60-kilo batteries. And the outer gloves and cameras and everything else.
Yeah, which would be nice to have brought back to Earth, wouldn't it? There's a lot of censorship at the moment. And NASA must be getting very nervous because the longer they take to launch their SLS rocket, it's only been in construction for 12 years, and testing it for 5 years, you think they've got it sorted by now. Oh, they've got a hydrogen leak. Why are they using hydrogen? They didn't use hydrogen on Apollo. They used liquid oxygen and kerosene. Hydrogen is the Houdini of gas. It can't be constrained. It can't be restrained. It's so small, it keeps getting out.
Musk is using methane and getting twice the thrust. The ones he's using are 500,000 pounds apiece. The ones on the SLS are 200,000. They're getting all their boost off the solid rocket.
That's right, yeah. Those solid rocket boosters are quite old technology. I mean, they were developed by Jack Parsons 60-odd years ago as jet takeoff assistance for heavy loaded bombers. They put these little solid boosters on the side to get the plane up in the air. So they're using 60-year-old technology. I mean, it sounds all very impressive, and it looks very impressive when it takes off because it produces all this great clouds of whatever it produces. And maybe it works. And the trouble is you can't switch them off. Once those solid fuel boosters are ignited, that's it. They've got to burn out before they'll stop.
Well, you got the other problem. I mean, if you got ones that you could turn off, how are you coming back down? You don't have wings.
And you parachute down. I mean, that's why they have to be rated for human spaceflight. It's all very well putting instruments on board. It doesn't matter if it crashes. You can always put more instruments on board. But you've got trained astronauts on board. You've got to ensure their safety. But if they can't ensure their safety, they're not going to fly.